Welcome to Polymers 2. This is the second lecture on polymers, and I'm going to continue where I left off last time. So let me just repeat the objectives of the series of polymers. There are 5 main objectives that we are going to that we have, and that is fundamentals of polymer science and technology would be extensively discussed in these series of polymer lectures. That we are going to take a look at thermoplastic polymers, thermosetting polymers, elastomers, and polymer recycling and biodegradability. So these are all the important topics that we are going to discuss as we started last time, and we extended to this lecture and the next the third polymers. But this is Polymers 2. Let me tell you about a little bit about the crystalline structures that is formed in some kinds of polymers. Both amorphous and crystalline structures are possible. The tendency to crystallize is much less than for metals and or non-glass ceramics, but it is higher for the cases of polymers. Of course, not all polymers can form crystals. You're not going to have 100% crystalline polymer, so there would be a degree of crystallinity, and that's the proportion of crystallized materials in the mass, which is always less than 100%. How does it look like at the molecular level? The folded chain that you see up here starts, when this within I'm encircling it. That is a model of a crystalline polymer, or a crystallized region in a polymer. Again, we have long molecules. That's the characteristics of the polymer molecules, and they are randomly mixed. And somewhere in between, we are going to have a long molecule that kind of like folded together, and that's really what this is all about. And then in the region, in the particular crystalline region, we are going to have something that's formed a crystal, as you can see, part B under here. Okay, so again, why do we care about crystallization? Why do we try to have it or not have it in polymers? The reason is because it's going to affect the characteristics and properties of the polymer. As we have more crystals in a polymer, we are going to have higher density. We're going to make the polymer, the material, become stiffer. Of course, you're going to increase the strength, and the toughness would increase. So it's not a bad thing to always have. Sometimes we want the polymer to crystallize, to increase all these properties that I'm discussing. The heat resistance would increase, and if the polymer is transparent in the amorphous state, then it becomes opaque when partially crystallized. Again, these are some of the properties associated with the crystallization of polymers. An example is shown here. This is for the polyethylene type. As you can see, the degree of for low density, the degree of crystallinity is 55%, and the degree of crystallinity for high density is 92%. The specific gravity is 0.92 for low density and 0.96 for high density, respectively. Modulus of elasticity would increase from 104 to low density to high density to 700 megapascal, and the melting temperature would also increase by 20 degrees Celsius by about 40 degrees Fahrenheit. Some observations about the crystallization process. The linear polymers consist of long molecules with thousands of repeated merges. That's the characteristics of polymers. And the crystallization, as I've looked at previously, it folds these long chain of molecules up on themselves. The crystallized regions are called crystallites, and again, we can have it in the randomly mixed we take the form randomly mixed in amorphous material. A crystallized polymer is a two-phase system. It's really important to realize. Some factors are involved in crystallization. Slower cooling. If we don't want any crystallized to be formed, we need to avoid slower cooling, because slower cooling promotes crystallized formation and growth. It's going to affect the mechanical deformation, as in the stretching of a heated thermoplastics, it tends to align the structure and increase the crystallization. Plasticizers, these are the chemicals that we add to soften up the polymers. That would obviously reduce the crystallinity of the polymer. The thermal behavior of polymers is of concentration on this particular slide. So let's take a look at this graph here that shows specific volume on the y-axis, the vertical axis, and the temperature on the horizontal axis. And you see there are two temperatures here, T sub G and T sub M. They're important temperatures because they pretty much gives us different regions of the curve. Above the T sub M, as you can see, for amorphous polymer, this would be completely liquid. In this region between T sub G and T sub M, we can have partially crystalline polymer, and we can have 100%, well, a little bit slightly below 100% crystalline polymer. And that would also mean that the specific volume would also be different. So as you can see, temperature plays a very important role here. In summary, specific volume is shown here. Specific volume is the inverse of density. So it's 1 over density as a function of temperature. So as we are affecting the density, as the material becomes, this is the inverse of that. So, if the density is pretty high, then 1 over density is pretty low. And that's why as we're increasing the density, the specific volume actually drops. So these are the regions of increased density, because specific volume is defined as an inverse of density, 1 over density. So increased density means lower specific volume. And that's what really this graph is all about. If we can have different types of additives in polymers by function, and just in general, properties of a polymer can often be changed if we combine it with additives. We can alter the molecular structure, or we can pretty much transform a polymer into a composite material by adding a second phase. There are different types of additives that I'm going to go over here by function. For example, the filler strengthened polymer or reduce cost, that would bring that's a filler that's added. Plasticizers, these are primarily soften the polymer and improves the flow, whereas the first one, the fillers, they make the polymer stronger, and it becomes much cheaper, because fillers are usually bring the cost down. They're cheaper than the polymer itself. The colorant, it would use for dyeing the polymer, and the lubricants, they would of course reduce the friction and improve the flow. There are also flame retardant. These would reduce the flammability of polymer. There are also cross-linking agents for thermostats and elastomers. Remember, I talked about cross-linking last time. And there are ultraviolet light absorbers. This would reduce the degradation from sunlight. Remember all the problems that we have. And that was one of them with polymers, is some types of polymers, they don't do well in sunlight. So we need to, they degrade in sunlight. So we need to have ways to reduce that, and ultraviolet light absorbers seems to help with that. Antioxidants this is not to be confused with the antioxidant that we use for the body. These are engineering terms, not medical terms. So antioxidants, they would also reduce the oxidation damage. Actually, antioxidants in the body, they're pretty much doing the same thing. They're reducing the damage that is associated with the free radicals. This is not a medical class, so let me concentrate on the topic. TP, or thermoplastic polymers, they can be heated from solid state to viscous liquid, and then we can cool it back to solid. We can repeat this many times without really damaging it. And of course, this is because of the molecular structure and macromolecules of the thermoplastic polymers. They have both linear and or branched macromolecules, and they do not cross. That's why we can do that. Thermostats and elastomers, on the other hand, they would be altered chemically when we heat them up, and we cannot bring it back to, if we take the thermal load away, we cannot really bring it back to its original shape. We cannot really recycle these, and the way the term recyclable is defined. This is because of the cross links with molecules and what we have went over last time. Some mechanical properties of thermoplastics are noteworthy here. They have low modulus of elasticity or stiffness. E is, of course, much lower than metals and ceramics. That doesn't provide them with the attraction that they need to apply as a material when we need the strength. So they become less attractive in that department. They have low tensile strength. It's about 10% of metals. They have much lower hardness than metals or ceramics. However, they have greater ductility on an average, and that would be somewhere between 1% to 500% or more for polypropylene. So let's take a look at the strength versus temperature diagram. The crystalline polymers, again, we are having two temperature here, T sub G and T sub N. We have deformation resistance drawn on the vertical axis and temperature on the horizontal axis. If we increase the temperature when we get to the range of T sub G, to the left of that, it's a low temperature. This is a solid or glassy region. As we are increasing that, and of course, for different type of polymers, either amorphous or crystalline or partially crystalline, you can see that the crystalline has a much higher deformation resistance, and as you can see, the amorphous polymer, they have lowest deformation resistance, and the partially crystalline polymer, it falls somewhere in between. That's the middle line. These are all the illustration of what we have already looked at. So let's take a look at some of the physical properties of thermoplastics. They have lower densities than metals or ceramics. That's expected. The typical specific gravity for polymers are somewhere between 1.2. It's approximately 1.2. Ceramics are 2.5. Metals are the highest 7. Much higher coefficient of thermal expansion is associated with thermoplastics. The coefficient of thermal expansion is roughly 5 times the value of metals and 10 times the value for ceramics. Much lower melting temperatures and the insulating properties, both thermal and electrical, and the much higher specific heat than metals and ceramics. Those make these materials very attractive of many different applications where all these properties are needed. So Some of the thermoplastic products, molded and extruded items, fibers and filaments, films and sheets, packaging materials, paint and varnishes. Of course, the plastic materials are normally supplied to the fabricator, and they come in the form of powder, or they're in bags in the form of pellets, drums, or larger loads by trucks or a rail car. The most efficient way of delivering them, and not through the pipelines. The thermosetting polymers are distinguished by their highly cross-linked three-dimensional covalently bonded structure. The chemical reactions associated with cross-linking is called curing or setting, and as we have discussed previously, they are macromolecules when these parts are formed together on these very big molecules, and always amorphous and exhibit no glass transition temperature. General properties of thermostats is also noteworthy here. They have the modulus of elasticity of thermostats. They are 2 to 3 times greater than thermoplastics, so they make them more rigid in comparison to thermoplastics. They're brittle. Virtually, they have no ductility. You probably experience some of these plastics that they break easily. They're less soluble in common solvent than thermoplastics, and they're capable of higher surface temperature than thermoplastics. They cannot be remelted, as I have discussed previously. They're going to degrade or they're going to burn. And there are 3 categories of cross-linkage in thermostat polymers: temperature activated system, catalyst activated system, and mixing activated system. Curing itself is accomplished at the fabrication plants that make the parts, rather than the chemical plants that supply the starting materials to the fabricator. So we have a chemical plant, we have a fabrication plant. The fabrication plant is where we actually put these together, and we make them into the shapes that are desirable. The temperature activated system, of course, as the name implies, they caused by heat during part of the shaping operation in the fabricating plant. An example is molding. The material started as a linear polymer, and gradually, when heated, it soften up for molding, but continuous heating can cause cross-linking that I have discussed previously. So it's very important to control the temperature accordingly. This applies to most common TS systems, and of course the term thermoset applies best to these polymers. Let's take a look at catalyst activated systems. In these systems, cross-linkage occurs when a small amount of catalyst is added to the polymer. Of course, this is in liquid form. Without the catalyst, we have a stable polymer. It remains stable and liquid, and these catalysts, they cures and change it into a solid form. So we cannot really change it into solid form, and then we add these catalysts when we need to. Okay. And there are mixing activated systems. In that case, we mix 2 chemicals, and we are going to have a chemical reaction. It forms a cross-linkage solid polymer. This is we use. Sometimes we increase the temperature to the levels in which we can accelerate this process. And the best example are most of the epoxy. So, in summary, TS versus TP polymers. TS plastics are not as widely used as the TP. One reason is it has higher processing costs and the complications involved during the curing. The largest market shares of TS is about 6% of the total plastic market. Some of the examples of TS products are countertops, polywood adhesives, paints, molded parts, printed circuit boards, and other fiber reinforced plastics. This brings me to the end of our today's discussion. If you have any questions or comments, feel free to send them my way via the course website. Thank you.